Here we have an example of a projectile. We got on page 152 in your book, number 4. It says a player kicks a football from ground level with an initial velocity of 27 meters per second at 30 degrees above the horizontal, assuming no air resistance. Find the following: the ball's hang time, max height, and range. Alright, so we got this object being kicked 27 meters per second at an angle of 30 degrees. We're going to start listing the information we know. We know that in the y direction we have acceleration negative 9.8 meters per second squared. The x direction is going to be 0 meters per second squared. The y direction's velocity, the component of the velocity over here, that's opposite, so we're going to use 27 sine of 30, and then we're going to use cosine of 30 for the x component. Now that y component is upward and the x component is to the right, so both of them are going to stay positive. We also know that from the beginning all the way to the end, the total displacement is going to be equal to 0. Now when we find the max height, we're going to find the point up here, so therefore the displacement is not going to be 0 there. It's going to be displacement 0 from beginning all the way to the end. Alright, so the hang time. We have the acceleration, we have the initial velocity, and we have the total displacement in the y direction. And really time is going to be determined by the y direction because that's determines how long it's going to be in the air when it goes up and comes back down. The horizontal displacement is not really going to affect, and the horizontal velocity is not going to affect how long it's in the air. So we're going to use the y direction information, acceleration, initial velocity, and displacement in order to find time. We're going to use this equation. Displacement in the y direction is going to be equal to 1/2 times acceleration in the y direction times time squared plus the initial velocity in the y direction times time. Plug in the information that we know. Half of negative 9.8 is going to be negative 4.9, so 0 times negative 4.9 times time squared plus 13.5 times time. We're going to factor out one of those t's, and that leaves behind negative 4.9t plus 13.5, and that t is out front. Now I've got two numbers that multiply together. I've got this t and this term right here. They multiply together and they equal 0. The only way that two numbers can multiply together to equal 0 is if one of them equals 0. So we're going to set each one of those equal to 0. So either time equals 0 or negative 4.9t plus 13.5 equals 0. Now time equal to 0, that's over here on this side. We're not really interested in that point. We want to know the point on the other side, and the time where it's going to be equal to 0 over here is going to be found by using this equation. So we're going to subtract 13.5 from both sides, and then we're going to divide by negative 4.9, and that gives us a total of 2.76 seconds. Now because we're dealing with a parabola, we got two different times when it's at that same height, that displacement equal to 0. That was at the beginning, which was 0 seconds, and that's also at the end, which is 2.76 seconds, and that's the one we're interested in. To find the maximum height, we're going to be looking in the y direction again, so we need the y direction information. Displacement in the y direction is what we're looking for. Acceleration in the y direction is negative 9.8. The initial velocity in the y direction is 27.0 sine of 30, which is 13.5. Now, there are a couple things we can do here. We could take this time, and technically we could divide that by 2 because that's halfway through the parabola. But that only works in this example because it's symmetrical, because I have the same starting point and ending point as far as the height. If I divide it by 2, then yeah, that works. However, I want to show you a way that works every single time. Now, the y velocity, it starts at 13.5 going upward, but it loses 9.8 meters per second every second. So the velocity in the y direction is going to be equal to 0 when it gets to the top before it starts coming back down. So I know the final velocity in the y direction is going to be 0, and that's my three pieces of information: the acceleration in the y direction, initial velocity in the y direction, and the final velocity in the y direction. So we're going to use this equation. Final velocity in the y direction squared is going to be equal to initial velocity in the y direction squared plus 2 times acceleration in the y direction times displacement in the y direction maximum, and that's what we're looking for. Alright, so we plug our 0 in for final velocity, we plug 13.5 in for our initial velocity, and then we plug in negative 9.8 in for our acceleration. 0 squared is 0, 13.5 squared is 182.25, and then 2 times negative 9.8 is negative 19.6. Subtract 182.25 from both sides. Then we divide by negative 19.6, and that gives us our max height is 9.3 meters. Now, if you use the time and just divided it by 2 and figured out the height from there, you would get the same answer. Next thing we're looking for is going to be the range. Now, The range is the horizontal displacement. So we need the velocity in the horizontal direction, but we also have the acceleration in the horizontal direction. But if you notice, we don't really have any other information other than the time. Now, ordinarily, I try not to use a calculated answer to find another calculated answer because you get some rounding error in that. But in this circumstance, I don't have a choice. I need the time in order to find the range. So the displacement in the x direction is going to be equal to 1/2 times acceleration in the x direction times time squared plus the initial velocity in the x direction. Acceleration is 0, the time is 2.76, the velocity in the x direction initially is going to be 23.4. Now since acceleration is 0, that part of the term completely goes away, and we get 23.4 times 2.76, and that equals 64.6 meters. Alright, so now we're going to do a scenario where it's kind of the same thing, except the only difference is we're going to be kicking the ball at a 60-degree angle. So the player in the previous problem kicks the ball with the same speed of 27.0 meters per second, but now it's going to be at a 60-degree angle from the horizontal. And we're going to assume the same stuff, no air resistance, and then we're going to figure out the ball's hang time, max height, and range again. Alright, so this time it's going to go at a steeper angle, 60-degree angle. Alright, so we're going to list all the information we know. We know the acceleration in the y direction is negative 9.8. We know the acceleration in the x direction is 0. We know the initial velocity in the y direction is now 23.4 because it's going to be 27 sine, which is still the opposite, and it's in the positive direction. And then the x direction is going to be the adjacent, which is cosine, so 27 cosine of 60, and that gives me 13.5. Now if you notice before, these two kind of switch. By kind of, I mean they do, because the sine of 60 and the cosine of 30 give you the same thing, and we had cosine of 30 over here on the previous problem. So essentially we get 27 sine of 60, which was the same as 27 cosine of 60 for the x direction on the previous problem. So those two velocities essentially switch. And then our displacement in the y direction is going to be equal to 0 again. Alright, to find the hang time, just like before, we have the acceleration in the y direction, we have the initial velocity in the y direction, we have the displacement in the y direction. We're looking for a time. So we've got displacement in the y direction is going to be equal to 1/2 times acceleration in the y direction times time squared plus initial velocity in the y direction. Plug in the information we know. Half of negative 9.8 is going to be negative 4.9. And then we're going to factor out one of those times again because that is a common factor between these. And again, we have two numbers that multiply together that equal 0, so we're going to set each one equal to 0. Again, this time right here is the one at the beginning. That's not the one we're interested in. We want to know this one over here. So we're going to subtract both sides by 23.4. Then we divide by negative 4.9, and we get that our time is going to be equal to 4.78 seconds. So it takes a total of 4.78 seconds to get over to the other side. In order to find the max height, we're going to do the same scenario here also. We know the acceleration in the y direction, we know the initial velocity in the y direction, and our final velocity is going to be 0 in the y direction because the velocity in the y direction decreases by 9.8. Now we still have an x component to the velocity the entire time. That doesn't change because there's no acceleration in the x direction, but the y direction goes to 0 when it gets to the top and then comes back down. So we're going to use the final velocity in the y direction squared. It's going to be equal to initial velocity in the y direction squared plus 2 times acceleration in the y direction times displacement in the y direction maximum. Final velocity is 0, initial velocity is 23.4, and acceleration negative 9.8. We're going to subtract both sides by 547.56. Then we're going to divide by negative 19.6. And we get that the max height is going to be 27.9. Again, we could have taken the time and divided by 2, but I want to show a way that would work every time, even if it's not symmetrical. The range. In order to find the range, we're going to have to look in the x direction. Again, we have the acceleration, we have the initial velocity, and we're going to have to use the time. So displacement in the x direction is going to be equal to 1/2 times acceleration in the x direction times time squared plus initial velocity in the x direction. Plug in everything we know. Since acceleration is 0, that part's going to go away. 13.5 times 4.78, and that gives us 64.5 meters. Now if we look at these two scenarios, we know we have the same acceleration in the y direction, same acceleration in the x direction. You notice the initial velocity of the components switched from 30 degrees to 60 degrees because essentially they were complements of each other and the total displacement was 0. You can see that the hang time is obviously going to be larger for the larger angle because the vertical component is bigger. With a more velocity vertically, that means it's going to be in the air longer. The displacement in the y direction maximum, the max height, is going to be greater. Well, if it has greater velocity in the y direction, it's going to go higher, obviously. But what's interesting here is that the displacement in the x direction, the range, is going to be equal. And that's because what happens is essentially with a smaller vertical velocity but a greater horizontal velocity, it's in the air for a shorter period of time than the higher angle, but it also has a greater horizontal velocity. So it goes further because it goes faster, but it doesn't go as far because the hang time is not as much. For the 60-degree angle, we have a large hang time, but we don't have a very large horizontal velocity. So essentially what happens with the horizontal velocity being large here and the hang time being small, and then a small horizontal velocity and a large hang time over here, they basically compensate each other and you get the same range for these two. And that's only with two angles that are complements of each other. So essentially what we're looking at is if the object if the projectile starts and ends at the same height from beginning to end and has the same initial speed, whether it's 27 or whatever, if the angles are complements of each other, they will have the same range. So that brings us to this. If we have a 75-degree angle or a 15-degree angle, as long as it starts and ends at the same height and they start with the same initial speed, if they're both 30 meters per second, then they will go the same range either way. And then you get 60 degrees and 30 degrees will go the same range, and you get your maximum range at 45 degrees. So if you ever want to kick something as far as you possibly can, you want to kick it at a 45-degree angle because that's going to be the maximum range you can possibly get it. You increase from 15 to 30 to 45, it increases, but then as you get to 60 and 75, you don't have as much horizontal velocity, so it doesn't go as far. And that's why you have the two complements having the same range. So the 15, the 75, the 30, and the 60, and then 45, and obviously 45 would have the same range as well.